Hello and welcome back to this Common Lisp tutorial series. We're going to have a look at Lambda functions today. This is going to conclude for now our exploration of functional programming. I imagine we will be revisiting it at some point in the future, but for now this will be our last video. We've done 5 weeks of functional programming and I think it's time to maybe look at something else in Common Lisp. I won't say too much about that right now. However, I am working on some very things I think and hope you will find very interesting, and we will see those in another week. But today, Lambda functions. Lambda functions are not unique to Common Lisp or Lisps in general. JavaScript has them. Python has them after a fashion. They're just functions. There's nothing special about them. They're values. In languages like this, we have functions being treated no differently from data, and especially in Common Lisp where code is data and functions are just code. Everything is just, objects at the end of the day. But let's have a look at one. The anatomy of a lambda expression. Let's get that and print out what it looks like. So we've got this lambda. I'm going to define a square function because they're nice and simple to remember. So we just take an x and we return the result of multiplying the x by itself. And if we print that out, we get this function lambda x thing here at the bottom. So this is just a value, just like anything else. They take lambda as their keyword here. We would see something like defun followed by a name. A lambda function does not have a name, so this lambda tells us this is an anonymous function, which is another term for lambda functions, is anonymous functions. They take an argument list, just like anything else, and they take a body, a function body. And in that respect, they're exactly the same as functions, they just don't have a name. And because of that, you can use them in place. We can take something like map car and we can pass in lambda, and again we'll use the square, and we can pass it a list of numbers, and we will get our squares there at the bottom left, that 1, 4, 9, 16 and 25. We might want to use a lambda function here if we're using something super simple and we don't care about reusability because it's a one-time thing and we don't want to define functions everywhere. It might be a very specialist operation and it makes no sense defining a function and polluting the global namespace with that, or the package namespace or whatever it is. So we might just want to use something here, and we could do the same. Map car. No, we're going to say reduce. It's going to take a lambda, and because reduce takes a and b, we're simply going to multiply a and b. I'm going to pass in a list of 1, 2, 3, 4, and 5. There we get 120. We had a look at this example earlier, and in fact, this is realistically no different from passing in, this. Sorry, I forgot a quote there. Let's abort that. There we go. It's exactly the same, but if we were going to do something a little bit more esoteric, like we multiply, maybe not esoteric, but we add 1 to the result of multiplying them together, we get 206. So we can put a specialist lambda function in here to plug into our map car and reduce functions, and any function that accepts a function as a parameter, a lambda, can be used there because they're just functions. There's nothing inherently special about them except the fact they just don't have a name. And because of that, I hope you're liking having notes here. It's helping me keep on topic a little bit. I do have a tendency to ramble and lose focus. So what we've got here is we can actually immediately invoke a function, and that might seem a little bit strange. So if I turn to my notes, because I was making notes about this, because we know in Lisp, an unquoted list, so a quoted list is one with the quote there at the beginning, but an unquoted list is a function call in effect. We can actually say lambda, and we'll take an x, and we will actually, take a y. We'll actually add y to itself. Now, because this is a lambda function, and we're trying to invoke it, we can pass in 9 here. So I'm going to say 9 plus 9. We get 18, of course. And this is immediate invocation. So this expression evaluates to a function. So that goes into the first position of our list here. So that equates to a function call, and this is the second parameter. And so we can use this in place immediately. And we could, let result be the result of this expression. We'll just print result. As you can see, we get 18 printed out there. So that's pretty cool. You can, if you've got, a complicated function that you need to calculate something, you could do it in line here just to get the result if, again, it's a one-time thing. We can also chain these things. So if we, again, do this immediate invocation with a lambda, we're going to take a y, and we're going to do the same thing. We're going to add y to itself, and we return that. But instead of a second parameter, we're actually going to do a second invocation. So we're going to take an x this time, we're going to square it, and that is going to take a 9. And I'm really hoping that I've got this right. There we go. Yeah, there we are. So we actually have 162 here. So we're taking 9 in into the first thing here, because this gets evaluated as a function call, because we've got these surrounding parentheses. And that goes and looks at its first argument, which is actually an immediate function call, again, to another lambda function here, which takes an operator. So the 9 goes into here, and we get 81, and this evaluates and gets replaced with a value, which this function then operates on. And I'm not entirely sure, practically speaking, that you would ever use this. I certainly haven't. But because of the rules of the language, there is nothing stopping you from doing this, and in fact it's entirely consistent with the way the language works. And we can actually do some interesting things here. We can actually bind these things to symbols. Def parameter. Well, I'll not do a def parameter, I'll just use another let, because lets are nicer, I think. There we go. So we're actually binding this function expression, this lambda expression, to this symbol called square, and we can apply to square the list of 9, and we get 81. Remember that you're applying an argument list to a function. You could use a fun call as well if you wanted. And if you wanted to use def parameter, you could use def parameter. There's nothing about these, you're just binding a symbol to a function here. In effect, this is like a localized flet, I think. I'm not sure, I'd have to investigate a little bit further to find out if it behaves like flet or if it behaves like labels. I'm not sure of how the recursion would work in this context, and now is not really the time to go explore and find that out. But we can also, because we can bind them to symbols, we can actually have and again, we don't have to do anything crazy with these functions. We're just keeping it nice and simple. It's just squaring it, because the behavior of these Lambda functions doesn't matter. Anything that you could do with a regular function, you can do with a Lambda. And indeed, this is what actually we're doing here. We're defining a function called fn, and it returns a function. So we can say apply. We're going to call fn, and that call, we'll use 8 rather than 9. That call is going to substitute for this lambda that is doing a square here, and I will need to remember to compile that in, because that catches me out sometimes. And when I do this, we get 64, because when we do that, we basically get this lambda function, and we're applying the list of 8 to that lambda function, and we're getting that back. Of course, we could have this. There we go. Let me remember to compile that function again. I've got an unbalanced paren somewhere. Oh, there we go, that fixed that. Invalid number of arguments. That's straight. Yep, because I'm calling the wrong function. Silly me. Let's put that as fn2. There we go, so we get 81. So again, this lambda function is accepting 2 parameters, and we're applying a 2-parameter list to the return of fn2, which returns us a lambda function. Now there's some very interesting behavior that falls out of that. Because a function can return a function, what we can actually do is this. Sorry, excuse me. So if we evaluate that, you can see at the bottom left there that we actually have this thing called a closure, which is a way of trapping state inside this function. So if we were to bind this together, let add 5 be adder 5, I should be able to apply add 5 to the list of 5. I might get this wrong. I might need to use the hash quote lookup. But no, there we go. We can apply add 5 to the list of 5, and we are able to ensure that no matter what we pass in here to this x, this 4 here, in the context of this, that number is always going to be bound to the 5 here. So this is what's called a closure, and they say that because it's closing over a value. It doesn't matter what this is called here. This could be like still works. The name of the symbol it's bound to could be anything, but we know that this num, because of here, when the lambda function gets called, which is here, it's always being called with when num equals 5. But we could also do this. And we get 4 because in this instance we're binding a different instance, a different context of this lambda function to something else. And every time that we make a call to the return value of that, we get +2. So this is really cool, and it can build on some very interesting things, which is kind of sort of what we're going to look at finally here, is something called a curry. And I'll just type this out. Sorry, let me put that as args1. So this might look a little crazy. We have this thing called a curry, and curry returns a function that returns something. It returns a function that is the application of another function with some extra arguments, and that sounds pretty crazy. There's a difference between currying and partial function application, which I can't really get into for time constraints, but trust me. Let's say we have this function called exponent. So 2 to the third power is 8, so 2, 4, yep. Now what we might want to do is curry this function, and that means that we can turn a function of 2 arguments into 2 functions of 1 argument. So we might say there we go, it's the expert. It's the result of curry and then we can say C expert 3. Yep, that's because I've done something a wee bit wrong there. Yes, I need to apply it. My bad. There we go. So what we've done is we've got this function here of 2 arguments. Takes a base and power. And with this defined curry function that we have here, which I'll break down in a minute, we can get a new variable, which is the result of currying this, and it applies the arguments. Now we could do something else here. We've actually passed the second parameter into this, and I believe, if my logic is correct, nah, it still needs to take an empty argument. That's fine. So we've got this this function here. It takes the 2 and the 3, and using the curry function, we pass 2 and 3 as rest parameters there, and that forms over and creates a closure here that we now have. And when we apply the result of this closure, we pass in an extra set of arguments, we can then use the apply function again on the original function passed in, which was this expert function. And then we use append to join the original argument list with the new argument list. And we can get the result. And it's through using this function and returning a function and using apply, we can simplify functions down. And it might seem a little abstract as to why you might do that, so I'll give you a little bit of an example here. Now, let's say that I want to do something in a a map car, but my function that I want to use in that map car takes more than one argument. We know that the function that map car takes one parameter only. So let's say we've got this square function, not a square function, some random function, defun something, takes an a, a b, and a c, and it returns the sum of a, b, and c. So it's just going to take 3 numbers, but mapcar can only give us 1. So what we can do is we can say let s be the curry, and we're just going to have it add 1 and 2. So we're going to say curry something 1 and 2. I'm going to make sure that's compiled in there. Let's say map car s 1, 2, 3, 4, 5. So we can see here that we've got 4, 5, 6, 7, and 8 because 1 and 2 is added to 1. So that gives us 4, and so on. And that's why we get different numbers. But here we can use currying to actually apply parameters to a function and turn it into a function of a different argument length that we can then chain into using somewhere else. So it's functions and objects, and functions being applied a little bit and getting a little bit more information and a little bit more information until you get a result. And of course you could put like 0 and 0 in here and we'd still get the same thing based on what we know the function is supposed to do. But for whatever hypothetical reason, let's say we just wanted to use this, we just pass in some values, partially apply it, understanding the behavior of the function, and then it just plugs in as ever it would. And it is Lambda that facilitates us using this, and that's pretty cool. So I appreciate that was a wee bit of a whirlwind tour through what Lambdas are, how you can use them, and you know, a little bit about what they look like, but there's not a lot more to them than that. And you can curry a regular function, which we did, but you could also curry a lambda, of course. Yeah, that is it. Thank you very much for watching. I hope you're all looking after yourselves, and I will see you in the next video next week.